Today, we're going to look at limits and continuity. We introduced the idea of a limit when we first started talking about finding the slope of a tangent line by approximating the tangent line with a secant line. And then we just started moving the 2 points on the secant line closer together to see if that slope was headed anywhere. So we started introducing the idea of a limit as the 2 points got closer together. What's happening to the slope as the 2 points get closer together? And then to have running in the background the definition of a limit, we wrote the definition of a limit, and I abbreviated it here. So the limit as x approaches a of f of x is equal to L if and only if for every epsilon greater than 0, there is a delta greater than 0, such that the absolute value of x minus a less than delta implies the absolute value of f of x minus L is less than epsilon. As x gets closer to a, f of x gets closer to L. More specifically, we can make f of x as close as we want to L so long as x is sufficiently close to a. So the epsilon is what you choose. We can make f of x as close as we want to L so long as x is sufficiently close to a. That's what we're saying in the definition of a limit. Now, I mentioned previously that I just want this running in the background. I want that idea that we can make f of x as close as we want to L so long as x is sufficiently close to a. I want that idea running around in the background. We can make f of x as close to L as we want. So long as x is sufficiently close to a. Epsilon is how close we want f of x to be to L. We just have to be able to find a delta that will make that happen. Then I just replaced all the words with symbols because we mathematicians, we all love to have symbols for things. Kind of comes out of laziness. I don't want to write for every single time. I also don't want to write if and only if every single time if I can get away with write just IFF. Dangerous in the time when we have autocorrect in typing because it'll read IFF as it'll want to replace that with IF, and that completely changes the meaning. If and only if goes both directions. If is just one direction. Let's take a look at an example and remind ourselves of what we do. In this case, we have the limit as x approaches 0. In this example, we have the limit as x approaches 0 of sine x over x. In this case, we can't plug in 0. This expression is, or this function is not defined at 0. But we can plug in numbers that are close to 0. So note, we can't plug in 0. Sine of 0 over 0 is undefined. So we can't plug in 0. But we can plug in values of x that are close to 0 to see if this expression is approaching some value. We can't plug in 0, but we can plug in values of x that are close to 0. So let's plug in a bunch of values of x that are close to 0. I'm going to take my function, sine of x over x, and I'm going to put it into my calculator, and then I'm going to look at a graph. A lot of times I see people say, oh, or we can look at a graph. When you're looking at a graph, you are plugging in a bunch of values of x. So plugging in a bunch of values of x, looking at a graph, same technique. So on this graph, it looks like as x is getting closer to 0, the values of the function are getting closer to 1. I'm going to check my zoom. Oops, my window. And on the y scale is a 1. So we're getting closer to 1. If I change my window and zoom in a little bit, I'm going to cut the vertical in half. It looks like that function is approaching 1. Now, if I try to trace this function, when we plug in x equals 0, we get no value for y because the function is undefined at 0. But if we plug in values that are close to 0, we'll get a value for the function that is close to 1. So in this case, if I plug in 0.1, I get 0.998. And on the other side, if I plug in negative 0.1, I get 0.998. That makes sense. Sine of x over x looks like an even function. I've got that vertical symmetry. Now, if I want to plug in a value that's closer, say if I plug in 100, then the value of the function is closer still to 1. And if I plug in a value that's even closer to 0, I get a value of the function that's even closer to 1. So the graph seems to indicate, that is, plugging in values seems to indicate that this limit is 1, despite the fact that the function is not defined at 0. So it seems, draw the function first, that this function, when x is 0, this function kind of comes up, is undefined at 0, but both ends, or from both sides, we are approaching 0. So the graph suggests that the limit as x goes to 0 of sine x over x is equal to 1. This is just plugging in values that are close to 0. So if I made a table of values, if instead of looking at my graph in picture form, we know that when we plug in 0, the graph is undefined. But then we're just plugging in values that are close to 0. So when we plugged in 0.1, we got 0.99833. When I plugged in 0.01, I got closer to 1 still at 0.99998. If I plug in 0.001, I just needed more digits. There are a bunch of 9s, 99999982. So it looks like, even though I can't plug in 0, it looks like as x approaches 0, it looks like the function is approaching 1. As the values of x get closer to 0, it looks like the values of the function are getting closer to 1. To fit the definition, if I can pick any value of epsilon, I can make sine x over x as close as I want to 1, so long as I make x sufficiently close to 0. So one way we have of figuring out limits is to just plug in values. Look at a graph, plug in values. Those are the same thing. One is just more visual than the other. Notice that we did not use the definition of the limit to calculate the limit. The definition is just to make sure that we know what we're talking about, that we're all going to talk about the same thing, that we're all going to mean the same thing, that we are able to quantify what we mean when we say that sine of x over x approaches 1 as x approaches 0. Any questions?
What's the definition of a limit? I don't understand the definition of a limit.
The definition of a limit says that the limit as x approaches a of f of x equals L. This is what it means when we say that the limit is equal of the function is equal to L. As x approaches a, f of x approaches L means that we can make f of x as close as we want to L, so long as x is sufficiently close to a.
Okay, that answers it. Thank you.
So L is what we are claiming the limit to be. So in this case, f of x is the sine x over x, a is equal to 0, and L is equal to 1. Any questions? The precise definition of a limit is always an uncomfortable thing to experience for the first time, and it's not a good way to calculate limits. In fact, it's not a way to calculate limits at all. Right. So this is, sometimes I refer to this as a brute force approach. We're just going to keep plugging things in until we find the information that we want. And we're looking down here. If we keep plugging in things that are getting closer to 0, we see that the values of the function are getting closer to 1. Any questions? Comments? Snide remarks? One place we use this idea of a limit where we just kind of keep calculating until we can see what's going to be happening is to calculate the slope of the tangent line. That was our motivation for coming up with this plan in the first place. It seems that you all trusted me when I just said, this is one of the important questions of calculus. And everybody's like, oh, all right, I guess this slope of the tangent line thing is important. I still haven't justified that, by the way, so keep an eye on that. Another place that we need limits is to define a concept called continuity. In natural language, continuity is kind of an easy thing to describe. So Newton originally described continuity as being able to draw the graph of the function without lifting his pen from the page. So Newton originally thought that was good. Actually, I shouldn't say that if he thought that was good or not. He might have known that that was wildly insufficient for any kind of rigorous treatment. So apologies to Newton. although not really. So a function can be continuous. Let's talk about continuity. Newton's original idea was that a function is continuous if I can draw the function without lifting my pen from the page. A function is continuous if I can draw the graph of the function without lifting my pen from the paper. So here's what happens. This quite possibly, you've seen this happen a lot. Someone says, this is how things work. And then they just start getting bombarded with what if. Yeah, well, what if this happens? Yeah, well, what if this happens? Well, what if this happens? And Newton's like, oh, the function's got to be continuous. And I'm like, oh, well, what does that mean? It's like, oh, it means I can draw it without lifting my pen from the page. And everybody was cool with that. But then we needed another level of continuity. But this is the first place we're going to use limits to help us define more precisely continuity. So if I start drawing a function, I just need the x-axis for this. Let's see, x-axis. So here I'm drawing a function. And so everything's all nice and continuous. I can have a sharp point, everything's cool. But now if I stop drawing the function here and then pick up the function down here and then continue to draw. So here's a point where the function is discontinuous. I'll call that, say, x1. So my function is discontinuous at x1 because I had to lift my pen up. I had to lift the pen up to draw the function down here. Another thing that could happen is that the function could head off towards infinity, and I can have some gigantic vertical asymptote. Let's say that vertical asymptote happens at x2. And on the left side, the function heads off towards infinity, and then on the right side, the function comes back from negative infinity. So once again, this fits. Once again, that fits. Because to draw the function, the function's discontinuous at x2 because we had to lift our pen up to start it back down here and continue on. Now, we have to remember that gaps in functions are actual gaps, even though we use little circles to describe them. So if I want to say that there's a hole in the graph, then I draw a hole. So here the function is discontinuous at x3 as well. Remember, the little circle represents a hole in the graph where the graph stops, jumps over x3, and then picks up again on the other side. So this does not violate Newton's definition by saying, well, you drew the circle there, just keep going around the circle and kind of keep going. That's not what we're talking about. And I think when people say, well, you drew the circle there, so it's connected, I think you know, I think people that bring that up know that they're being disingenuous in their question. Because that circle represents a gap. That's just how we represent. We want to make sure that everybody can see that there's a hole in the graph. So this function, let's call it f of x. We would say that f of x is discontinuous at x1, x2, and x3. F of x is discontinuous at x1, x2, and x3. Because in each case, we had to lift our pen from the paper to continue drawing the function, according to Newton. All right. So what we want to do is define continuity better than this. So here's how we can define continuity with limits. So first thing we want to notice that this function f of x is discontinuous at x1, x2, and x3, and it's continuous everywhere else. Fits Newton's description. We can keep drawing it without lifting our pen. There's only 3 points where we have to lift the pen from the paper. So we want to notice that continuity is a point-by-point thing. This is a thing that happens at a point. Discontinuities can happen at as small a location as a single point. So our definition for continuity will be centered around a point. So let's talk about the definition of continuity. A function, oops, I need a function. Continuity, now with limits. Now we need to bring some mathematical rigor to what's going on here. So we'll define continuity, but with limits this time. We could say that a function f is continuous. A function f of x is continuous at c if and only if the limits as x approaches c of f of x is equal to f of c. Pause for copying. A function f of x is continuous at x equals c if and only if the limit of f of x as x approaches c is equal to f of c. So we're actually saying 3 things in this statement. When I write the expression limit as x approaches c of f of x equals f of c, that includes 3 things that we need. Number 1, for a function to be continuous at a point, the function has to be defined at that point. So first, f is defined at x equals c. First thing that we need. Second thing that we need is that this limit has to exist. Otherwise, this statement is completely meaningless. So second thing, the limit as x approaches c exists. And the third thing that we need is these two values need to be the same. C is the point that we're defining, at which we're defining continuity. So the third thing that needs to happen, the limit is the same as the value of the function. Those are the three things that were including when we make this statement. If we're going to make the statement limit as x approaches c of f of x equals f of c, that means three things need to happen. One, the function must be defined when x equals c. Two, the limit as x approaches c must exist. And three, the value of the limit is equal to the value of the function. What this means is that when we are drawing the function f of x, when we get to c, we do not have to lift our pen from the paper. C is the point in question. Remember that when we looked at the function that was discontinuous, the discontinuity only happened at a point. So that's where we needed to define continuity, at a point. So C is a point where there's going to be where we're going to be in question. We're trying to figure out whether a function is continuous or discontinuous at a point x equals c. This is the requirement to determine that. So if we think back to the function, if we're drawing a function, and one of the things that can happen is that we stop defining the function one way here, and it drops down and then starts doing something else. So for example, if we had some kind of asymptote. So the one that we didn't include was that the function could have a hole in it, but still be defined. So here we have a function, and there are 4 places where the function is discontinuous. Let's label them x1, x2, x3, and x4. So we can see that the function is discontinuous at x1, x2, x3, and x4. Because at each of those points, we had to lift our pen from the paper to continue drawing the function. Even at x3, where we had this circle, That circle represents a gap where the pen jumped. X4 had it, the value of the function is way down here. There's a blue dot down there.
So it can be defined and discontinuous.
Yes, there are three things that are required for continuity. The function must be defined, the limit must exist, and the value of the limit must be equal to the value of the function. And each of these 4 points misses one of those pieces. Notice that x2 and x3, f is discontinuous at x2 and x3 because f at x2 and f of x3 are both undefined. So f of x, first note that f is discontinuous at these 4 points, x1, x2, x3, and x4. F of x is, or f is discontinuous at x2 and x3 because the function is undefined at those points. I did not draw any spot on those points. So f of x2 and f at x3 are not defined. We try to plug in x3, there's no value for x3. Note that f at x1 and f at x4 are both defined. So fx2 and f of x3 are both undefined. There's no blue dot at x2 and x3. Notice that f of x1 and f at x4 are both defined. Wherever the blue dot is, that's the value of the function. F of x1 and f of x4 are both defined. So I've got this part of the definition of continuity. The function is defined. The second part of the function, the definition of continuity, is that the limit exists. And that's why the function is discontinuous at x1. Notice that from the left, we're going to one value up here. And then as we approach from the right, we're going to some other value. So the problem at x1 is that the limit does not exist. So the limit as x approaches x1 of f of x does not exist. Because the left and right ends are headed to different values. We are never getting close to one value. So even though we satisfied the first requirement that the function is defined at x equals x1, the limit as x approaches x1 of f of x, it does not exist. Therefore, f is discontinuous at x1. Finally, if for x4, we see that f at x4 is defined and the limit exists, but the value of the limit is not equal to the value of the function. The limit says we're headed one place. The function says that place is no longer, is somewhere else. So at x4, f of x4 is defined and the limit as x approaches x4 of f of x exists, but they are not equal. The blue dot is not where it's supposed to be. So that's why I put the blue dot for x4 and I didn't put a blue dot for x3, because I wanted f to be undefined when x is equal to x3, but I wanted f at x4 to be defined. This is what happens. This happened in there's a very important historical documentary called Avengers: Age of Ultron. Now, what happening is that two people are headed to Sokovia from different directions, right? And the GPS says you are both headed to Sokovia, but everything is discontinuous because Ultron has removed Sokovia and started flying away. So the place still exists, but it wasn't where the roads the GPS told you it was going to be. I don't know if you watch documentaries, but I'm not sure that was a documentary. Any questions? So what we had was a great idea about how to define a continuous function. I haven't explained why we need continuous functions, but you're just going to have to trust me. This is an important idea.
Professor,
Yes.
how come for x1 the limit doesn't exist, but for x4 it does?
Because the limit exists if we're always getting closer to some value. So if this blue dot is at a height of 10, then the function is from both sides getting closer to 10. But if this dot is at 10 and this blue dot down here is at 5, from one side we're getting closer to 10, but from the other side we're getting closer to 5. We're not approaching any one value.
Oh, okay, thank you.
So they can't lift the pen off the paper, or can draw it without lifting our pen off the paper, is a very good intuitive idea for continuity. But when we need continuity to be rigorously defined, that starts falling apart. And not for trivial reasons like, oh, just make a spot and make it go all the way around, then you can keep the pen in contact with the paper. This is not some bar trick that we're trying to do. We're trying to define things so that we can use math to communicate to each other. We're not trying to win a bar bet. So it gives us a great intuitive idea of what we mean by continuous, but it doesn't hold up to any kind of rigorous scrutiny. So we need to define what we're talking about. Like I said yesterday, in math, the words need to mean something. That's just not true in like most other places where we use language. My favorite misapplication is the concept of the reasonable person. There's not really any such thing as a reasonable person. Great thing is, we can there have been plenty of studies designed to show that reasonable person, what an outside observer thinks is a reasonable person, does not really exist. It's an unreasonable thing to assume that an outside observer can look at a situation and decide what a reasonable person would do. You know what I mean? Like we always talk about fight versus flight. We forget about the other ones. Fight, flight, Freeze, friend. There's a lot more F going on there. And you see this all the time. Some situation happens and someone's like, oh, well, if I was in that situation, I'd do this. It's like, no, you probably wouldn't. Most of the time someone is saying that, they wouldn't do the thing they think they would do. You know what I mean? I should have been a crab scuttling. That's really what it comes down to. All right, let's pause the video here. Remember, this only seems like a lot to remember because it's a lot to remember, and you have to remember all of it all the time in perfect detail. We're talking math here. It's a very precise language. We have to know what we mean when we say something because the words that we use have a very particular meaning. The symbols that we write down have a very particular meaning. So, very precise language. That's why it's hard to learn. Any questions? Comments? Snide remarks? All right, let's pause the video here. We'll do our first sign off, and then if you have any questions, you can ask them of me in the unrecorded time. So that's going to do it for today. I will see you all on tomorrow when we start talking about continuity and its big brother, differentiability. I'll see you all on tomorrow. Everybody have a good day, and thanks for playing.